Welcome, everybody. We are going to get started in just a second. We'll let everyone filter into the room. All right, we are going to get going. Welcome, everybody, to our fourth and final webinar in our summer webinar series. My name is Michelle Berry. I'm the Stormwater Coordinator with Chesapeake Stormwater Network. Today, we're going to be hearing from Dr. Shirley Clark at Penn State Harrisburg, and she will be presenting on the urban soil conundrum, compaction versus water quality and quantity treatment. Before we get started, we are going to go through just a couple ground rules. This webinar will be recorded. So after the webinar, the presentation and the recording will be up on our website for you to share or refer to. We will also have a couple poll questions. So when we do the poll questions, they'll appear right on your screen. You'll be able to click onto your screen to answer the questions. Questions and comments for this presentation, we highly encourage those, and we ask that you put them in the Q&A. We will have time for a question and answer session at the end of the webinar. And if you have any comments or resources or anything like that that you want to share, you are welcome to use the chat. And as always, we appreciate your feedback on this webinar. We will have a survey link that will be put into the chat at the very end, and we appreciate any comments and things that you learned from the webinar that you would like to share with us. So we are going to do one quick poll question. How well do you know CSN, or Chesapeake Stormwater Network? Got the results coming in. Okay, great. It looks like we've got about 60% who's very familiar with Chesapeake Stormwater Network. That's always good to hear. And about 30% who knows who we are, but are not part of the network. And a couple people who have no idea. So I'm going to end the poll. And if you had no idea or are not part of your network, that is okay. Here's a little bit about our network and what it means to be a part of CSN. So CSN is a community of 11,000 stormwater professionals from the Chesapeake Bay watershed and beyond. We are here to provide free resources and training, capacity building, as well as to celebrate the successes and innovation in our field. So what does it mean to join the network? Joining the network is free, and it basically subscribes you to our About Monthly Stormwater Scoop newsletter, where we share resources and we celebrate innovations and successes amongst our community. And it also alerts you to our different programs and resources. So speaking of upcoming programs, registration for CUSP is now open. CUSP is a free professional training program that we do that involves speaker series, webinars, live and recorded, supplemental resources, as well as a chance to interact both with other members of your cohort as well as stormwater experts. So registration, like I said, is open now. You can find information on our website, and it will close September 4th. The actual courses will run September 6th through October 27th, but you will have time to finish the courses beyond that period all the way until December 15th. So if you are looking for any more information or have any questions about that, please feel free to email us and find more information on our website. So we're going to do one more poll before I introduce Shirley. I'm going to pull that up on the screen. All right, so here's a question relevant to our presentation today about turf grass. How many acres of turf grass do you think there are in Pennsylvania? Okay, got almost everyone who's clicked on the link. So yes, the answer is 2 million. So about 64% of you guessed correctly or knew the answer. And we had 31% who said 20 million, about 5% said 200,000. The answer was right in the middle there, 2 million. So we welcome Dr. Shirley Clark. Shirley Clark is a professor of environmental engineering at Penn State Harrisburg. Her stormwater research focuses on urban water quality and quantity treatment in urban landscapes, and currently is focused on shallow subsurface water movement and how that impacts flooding. And we're excited to have Dr. Clark present on this topic because we know that there's been a lot of interest amongst our network in soil health. And urban soils outside of stormwater control measures, like Dr. Shirley will be presenting on, are part of stormwater management. So understanding more about urban soils' ability to provide both water treatment and infiltration is vital to the work we do at CSN and to understanding our BMPs. So with that being said, Dr. Shirley, you are welcome to switch to your presentation.
Sure, I'd be glad to. I'm going to. So hopefully everybody can see the cover slide now. Again, I really appreciate this opportunity to present today. And I titled this the Urban Soil Conundrum, because there are many things we're asking our urban soils to do. And so when Michelle and David asked me to talk about soil health, I'm like, I'm not really sure we have a good answer for that one. So, but I do want to, before I get started, I want to acknowledge that this is coming from years of research and people that I've worked with over the years, and currently Bob Pitt, one of my colleagues, Zarana Mij, Reddy Saleshi, Jay Jalbathi, former grad student who's now got his PhD, Karan Jain, and I can't list all the graduate and undergraduate students who've worked on this over the years, but this is their thank you for all the, I get a chance to present their work and really show off what they've been doing. So let me come back in with this, and I just wanted to give you a thought process. When they approached me about doing urban soil health, I'm like, urban soil health is not the stormwater control measures that we have, but it is, again, really what we're asking of every place else that is not an urban, that is not a stormwater control measure in our urban landscape. This is our campus. I was just out walking around this morning to clear my head and be ready for the webinar, and you can get an idea on here as to exactly how much turf grass we have and how much turf grass we have to maintain. Pardon me. The red stars that you see on there are our stormwater control measures. And then it is a very small percentage of the land that we have. So what I'm going to put up here is this thought, is that, you know, when we talk about urban soils, we're really talking that we really are coming in, we're clearing land, we're doing development, may already be developed in a lot of the Chesapeake Bay watershed. And we want them to give us structural support because we want to have buildings that stand upright. And if we don't get that structural support, this is the Millennium Tower in San Francisco, they're having to drive new piles in to keep it from tilting over. So again, we want that structural support, but we also know that if we don't get this right, we can have sinkholes develop. What we're hoping for is over here in expectations, we get this nice manicured space. Often we'll use turf grass. We can discuss the health of turf grass. But what we really end up with is that we have this compacted soil in a lot of our urban landscapes that give us this challenge. And eventually what we're thinking, given all of this turf grass that's out there, we want to get to water quality and quantity mitigation in that urban landscape, because not every lawn, not every open space drains to a stormwater control measure where we can do this type of treatment that we've been designing for. So I'm just going to quote the CSN here. There's more than 9.5% of the watershed is turf grass. And looking at some of the county areas, you know, we're looking at these are the Maryland and Virginia counties. Many of those in suburban areas, they're 35 to 45% turf grass. So we are asking a lot of our turf grass, our urban soils, or we're ignoring them and not including them again. So it's about 2 million acres of turf grass statewide. That's not just the Bay watershed. So I put in here this kind of funnel that we're thinking about. We're asking for Structural support, so our homes are all level, we don't have cracking in the walls. We're asking it potentially if we're going to fertilize our lawns, we want water quality treatment. We would like to reduce the amount of runoff, so we want water quantity treatment. And out of this, we're actually hoping somehow we get to pre-development hydrology responses. So we're really asking a lot of our urban soils. So coming in with that, I'm going to start with water quality, which is where you got a chance to have my career. This is where I actually started. And please note, hopefully I've cited everybody correctly for whose pictures I borrowed. If I look at this, this is one that we're looking at a much healthier soil. And obviously you can see where the compaction layer is right here. And if I'm thinking about it from a water quality perspective, I really have about 9 inches of reactive media where I'm asking that soil, that healthy soil, to do something to reduce nutrients, to reduce metals, to filter out solids. And now what I'm looking at up here is, given this may be cut and fill, this may be a different soil, it may not be native, it may be compacted. I'm really talking about cutting this down to about 2 to 2.5 inches of reactive media. And what does that mean if I'm starting to think about water quality and I'm looking at infiltration and trying to prevent my pollutants from moving to the groundwater? And I'm going to come in with this. So when I think about physical filtration, I'm thinking about what is going to be captured at the soil surface as water infiltrates into the ground. And I put in some of the traditional cutoffs that we often use for stormwater. We'd like to remove 1 micron particles or smaller, or 10 microns or 20. And you can begin to see, media filtration, and soil is a media. Let's be realistic about it. It is a treatment media, and it is a reactive treatment media that it's acting as a media filter. You can see its very lowest limit is going to be around 1 micron, probably closer to 5 to 10 microns. And all of the stuff out here that is much smaller is not being removed, whether that's the nutrients, pesticides. So again, we're actually looking at, from a physical standpoint, we're not getting treatment of these things. So we have to assume, or have to hope, that we have a healthy soil that is reactive, that is providing some of that treatment. And I just want to come in and highlight with this some of the prior work that was done, is that if you look at this and we're thinking about physical filtration, our total phosphorus here, we can remove, in this case, about 82% of it if we can treat and filter out 5 micron particles or greater. But we started talking about nitrate, and we certainly know nitrate is a concerning pollutant in the Bay watershed. We are not going to do it by physical filtration. We have to have something going on either in the soils or in the turf grass that will allow us to do it. Even when we get to metals, which is closer to my favorite things, we can see this is the total concentration. This is the dissolved or less than 0.45 micron concentrations. And we can see again what the concentrations are and how much can be removed. But most importantly, what I wanted to show with this is the highlight of the gap. So for copper, a lot of it is going to be particulate and filtered out. But if we get out to thallium and antimony, and we had a project where we had to do it, or zinc, a lot of that is actually going to be zinc that is tied up into particles that are 0.45 microns or smaller. So to get those out of the water before it hits the groundwater, we need that reactive media, which means we need a healthy soil. And I did put in here, this is a summary from one of our papers, just to look at some of the nutrients. And when you look at that and you go back, and I am a chemical engineer by education, so that's the fun part to me. If you're going to do and remove ammonia, you either need to do some sort of ion exchange, or you need to oxidize it to nitrate and then try to remove the nitrate. Or you've got to be looking at plant uptake. Again, same thing for nitrate and nitrite. You're really looking at either an ion exchange, but we really don't have good anion exchange in soils, which is why nitrate tends to move. Or we've got to hope for plant uptake, which means we've got to capture it in the root zone. We're not going to get a lot of water bubbling back up and pushing water back up to get it back to the root zone. So phosphate again is a little bit easier because we can have a chemically active soil with iron or aluminum and things like that. Where we get we'll get some removal, or we can have that plant uptake. So those are just kind of the thought processes that we have to think about what are we expecting, not just out of our bioretention media, but I'm actually thinking about soils and providing some of that treatment also. So I do want to put in some of our research that talks about what should we be considering for this water quality treatment. And one of the things that we have done regularly, whether it's in urban soils outside of an SCM or the media inside an SCM, is to look at that impact of initial soil phosphorus content. And this is just some testing that we did where we actually separated a soil collected on a state game land into various layers. And this was, again, then our influent runoff concentration. And then this is going to be our soil concentration and then our effluent water concentration. And this is the O, or the organic horizon, that layer on the very top that's got a much heavier organic matter from decaying leaves. And then we start getting in here into our top soils, our A horizon, which does have some organics, does have some minerals. But you can see here the difference in initial phosphorus content in the soils, and you can see that there is a difference in the effluent water concentration. There's very little treatment in that organic layer. We're really relying on that A layer where we don't have that heavy concentration of organic matter containing phosphorus to provide that phosphorus treatment. So that's where we get to that phosphorus retention, is we need a soil. In that case, if we need phosphorus treatment, we need to be in that part of the soil where we are actually deficient in phosphorus for plant growth, and where this can then provide that phosphorus uptake and removal. And I did want to put this in here. It's a little on the busier side, but if you can focus again, particularly on the black dots, the total phosphorus here, we then looked at media's percent carbon, and we looked at, again, another look at that phosphorus concentration. And you can think of these as percent removals from 0 to 100 and 0 to 100. And you can see the black dots coming here and see how precipitously it drops off. We actually get negative removal of phosphorus if our organic carbon content ends up being around 10%. We actually lose it around 5%. So we're talking about percent carbons of being, less than 1%, 1 to 2% in order to have, or 0.1 to 2% to get good phosphorus uptake. And the same thing in here, when it's phosphorus concentration, we start seeing it drop off when the phosphorus concentration gets above about 6 parts per million. So how do we deal with this? There's a couple of ways. Obviously, in our urban lawns, we're not going to go out and build an SCM or try to treat it as SCM in every urban lawn. We may build it. Hopefully we all do. We have beautiful rain gardens at our houses that we can direct a lot of our flow to. But we can get it and think about soil depth as a potential design criteria. And so that's where that deeper, healthier soil works out. If I was trying to remove metals, my influent concentration, I can do it at any depth I've got between 1 to 3 feet. But if I start looking at needing to remove potassium, which we really don't, actually depth is a problem. Again, we get depth as a problem, and at least initially we get potassium washout. But with nitrate, I actually can get some removal at depth. And the reason is because while soil's not, this is actually a granular activity carbon, but anything we could work with in that respect, and soil will provide some of that, is that while soil doesn't remove a lot of nitrate in any single location, if we can actually get the depth, they actually have a lot of time for that contact and a lot of different spots on the soil where the nitrate could stick to if it was going to. I do want to provide some caution, though, with this information. When we actually did that testing, we had to, for one of them, actually break apart the soil and repack our soil columns. The other ones were taken out as soil cores and stayed intact. And if we came in with this and we had to disturb it and break it back up, we had a very high initial flush of total nitrogen coming out of these columns. So anytime we actually break up and tear up a soil, we start breaking up the cement, as a cementitious type or interactive bonds in soil particles, we're actually likely going to be releasing nutrients at least through multiple times, where we could call it a first flush equivalent, not of a storm, but of the age of the system. And you can see here, in the silt loam, again, they were very close in actually organic content and other things. This came out initially at about 170 milligrams per liter for several of them, and it got down below 50. And now we're over here, it started at less than 10. So these are the kind of things that we need to think about. The less we can disturb an intact soil, the better off we are for any kind of stormwater treatment that we want. With a caution towards this idea of breakthrough. This is actually done instead for copper, but I wanted to highlight that because this was a variety of loadings that we did. And after about 40 storm events, you can see that these two lines up here are getting very close. And what does that mean? It effectively, what it means is that we're done up in the top layer. So again, it has to keep going down. Now, if we get down to 10 centimeters, this is not full yet, but we got to watch that. This could be basically the soil is full and it's going to have to keep moving down. And we're relying on treatment at lower and lower parts of the soil profile to provide that. We did want to see if we could create some linkage in there between something we can easily send to a soils lab and measure, such as cation exchange capacity. Is that decreasing because metals are sticking on the soil or other things are sticking on the soil? And we saw as we really didn't see a great change. And so using cation exchange capacity to predict removal did not turn out to be as effective. On the other side too, we had done some testing in the laboratory with basically batch testing. We put some of the media in a jar and we shake it up and let it sit there. We were getting very good capacities there. When we started actually running them in columns like we would do in a lab to test media, the capacity was only about a third of what we were getting in the batch testing. And it's likely because in a column, you don't have the ability or the time for a pollutant particle to move to the inner parts of the soil and clear up the surface of the soil for new pollutants to stick. So that's probably a large part of it. So we need to think that batch testing in a lab for where that is actually now being translated to field work may not give us an accurate number for what the capacity is. It may be 25 to 30% of what we would get from a lab. So I did want to raise that as a consideration as we go through that. I did put a little flag up here. Again, it's a little bit chemistry heavy. But one of the things that we have done and begun to try to look at, we're still trying to figure out how to actually test it in the field, is that something they don't teach you in general chem, is that things like nitrate and phosphate and some of that ammonia will actually chemically react with like metals in the stormwater runoff, such as like, for example, from a car. And they create these complexes that are also much harder to remove because of both their size and of their chemical behavior. And that's the second part of the problem with that, is that may explain why some of our removals we see in the field don't match up to those wonderful lab calculations that people like me do. So that's going to be really a lot of our water quality issues, at least on the basic part. But I do want to tie up water quality with salt, because I certainly couldn't go without talking about road salt. And you can see that we very happily apply it. And he is smiling very well at that. And it's draining to our infrastructure, but it's also draining to our roadside soils. And so we've done a little bit of looking at road salts, and I'm just going to come in and say that. So again, the orange line here is our baseline concentration. And then we afterwards, we basically came through and we looked at both sodium chloride, which is very common, brines, as well as other salts that we could potentially look at, substituting out the sodium, because we know sodium has problems with soils, and also substituting out the chloride. And what we really see with that, if we look at the rate of uptake of nitrogen and phosphorus after just doing testing with stormwater, that was our rate. After when actually doing it with sodium chloride, it actually came up for nitrogen a little bit. That helped a little bit. But for phosphorus, we actually got releases once we started adding salts to that mixture. We actually got a phosphorus that had been previously trapped was actually released. And we see something very similar with the metals. Again, I'm more of a metals chemist at times. Again, we did see a decrease with the copper uptake, but importantly, what we saw was the zinc release. So again, what road salt does, and we know this from industrial chemistry, is effectively it cleans our media. And if you think about soil as a reactive media, if you think about your bioretention systems as a reactive media, if I was going to an industrial company that was doing this type of pollutant removal, what they would do is they'd put it up, and to regenerate their resins, their industrial resins, what they would do is they'd flush a load of salt through those things and collect what's left to get rid of the metals that were previously captured. So really soils are doing that. That's exactly what soils are doing, is they are effectively a urban resin, and that's what they're doing. And then we send road salt to them, and the top layer of soil is cleaned off, and then it pushes the metals lower where hopefully they're captured. But it does potentially accelerate the migration of pollutants towards our groundwater. Again, not immediately hitting groundwater, hopefully, if they're not that hot. The groundwater table's not that high, but it is accelerating that movement downward, and we do need to be aware of that, while still balancing it out with the fact that our public does like dry pavement. And I'm going to bring this up, again, some work we're doing in Lancaster. We've been looking at issues also around road salt and salinity movements. And these are, again, some of our soil sensors. And then the blue is the water sensor and our weather. And importantly, what you see is in this bioretention system, you see very sharp peaks because it's a very sandy soil. It was actually replanted, and it's a very sandy soil with dune plants in it. This is the one on campus, and what we see in here, you see how the peaks are nowhere near as sharp. It's a much siltier soil, and what it's telling us is that that soil is able to hold on to the salts a little bit longer, again, because the siltier soil is going to be a more reactive soil, and so that salt is being held onto. And you can see, we still see a residual salt concentration measured as conductivity out here, potentially now hitting the early growing season for plants. So if you've got plants in these systems, whether they're your roadside soils or whether you've got them in your bioretention rain gardens, you potentially could have higher salt loadings if you are working with a soil that has a higher organic load. It's more of a silty soil composition. And to start transitioning to the issue around water quantity, we've also done work looking at flow rates, and what we see, again, these are two different salt concentrations. And what we see is a very rapid decrease in some cases with flow rate as a function of, or as a function of how much salt we're putting on the soil. And what's interesting is you see this is the 150 milligram per liter, which is actually a very low concentration in road salt and snowmelt, versus the 1200, which is much closer to what we would see. We saw a much more rapid decrease at 150, likely because some of the salt is flushing through and not reacting. But you do see that rapid decrease in that flow rate. So salts actually, and the sodium in particular, reacts with the soil particles and displaces calcium magnesium, and it ends up creating almost a cementitious type interaction, and effectively what's referred to in the ag literature and in some of other places they've looked into this, effectively seals the soils. They've really looked at it as a function of the ratio of sodium to calcium magnesium. We also threw in the question around organic matter, and there is our soils itself, and then there it is with compost added to it. And again, so it's also a question, again, we talked a minute ago about this idea of how much organic matter or how much phosphorus, how much carbon do you have in a media? And while we balance it out with plant growth health, we also have to balance out the fact that we may have to think about where's the minimum on that side of it. We want the plants to grow. We want all of our vegetation to be good. But we also may need to balance it out with this idea that too much can cause multiple problems with nutrient leaching. It also can be reactive with the road salts that end up in these systems. So we need to be thinking about what are those balancing acts of our design criteria. And I know that that's where the states are going to take a look at this. So I'm going to shift now to a little bit more of our current work on thinking about soil as a water storage location or infiltration. So it is that balancing act between the two. So I'm back to my picture again, and you can see in here we have a nice healthier soil, deeper roots, likely to have a higher infiltration as opposed to this side. And now I've added my grad student who's now working in Virginia, but you can certainly see what the point I wanted to make is you can see how much runoff we're getting that is not infiltrating from our urban soils and running in there. And he was collecting stormwater for a project. So it was great that we didn't get much infiltration in that location on campus. Not really a good idea for urban stormwater management and flows into the system. So again, with that, and if we come back in and take a look at this still, I just wanted to highlight this is that this is modeling from Winslab and from Bob Pitt's work. On this media, on this commercial area, you can see we get a lot of contributions we would expect at the smaller rain depths from the impervious area that we already account for in our modeling, from our sidewalks, our streets, our parking, our roofs. But we do start seeing landscaped areas kicking in as once we get out to, that 2-inch storms, it's talking about 12 to 15%, and it gets even farther if we were to get larger storms, because effectively, and we do know this, is that we do know that in our larger storms, what we consider pervious areas are going to be contributing runoff. Again, in that perspective. So again, that's if it's on good soils, how much infiltration can we get? But if we're getting this compacted layer, what kind of an impact does that have? And that's really some of the work that we're focusing on now. Again, back to Bob's work and making sure, because I'm We love the graphs. And you can see in here again for the sandier soils research in Alabama versus the clayier soils, the models, whether it's Horton, whether it's green and amped, whether it's effectively curve number and antecedent moisture conditions, we're trying to, with those numbers, we're trying to account for the difference between dry versus saturated. And in the sandier soil, you can see dry versus saturated, but look at the impact of compaction on infiltration rates. And if you do it with the clays, again, the compaction makes a difference, as does the saturation. And in the sands, it's much more just the compaction. So really, the compaction is a huge issue. And again, we want compaction. I personally want it under my house. I would like my building to be standing up. I'm in a second floor office right now. I'd like the compacted soil. I'd like the soil beneath this building to be structurally sound. It was built by the military, so I'm in good shape here. But that is something to be thinking about. You know, there are places where we do want a compacted structural soil. I am not going to deny that. The problem is, of course, we talk about large scale land clearing. A lot of what happens is compaction over a much broader area where we don't want to have that compacted soils, because we are getting this impact on infiltration rates and potentially on then how much of rainfall becomes runoff. And I'm going to come back with that because I want to come back in and set this up in terms of thinking about it. Of course, when we get to nuisance law, you know, we can't damage the downstream neighbor's property. But I did want to just highlight some of the site development regulations. In Pennsylvania, for those who are from Pennsylvania, our pre-development condition, unless it is forest, is our assumption is meadow in good condition with hydrologic soil group B soils, curve number calculations for a 2-year storm event. In Maryland, curve numbers come into environmental site design calculations. If you're using a water quality volume calculation, you're multiplying precipitation by a volumetric runoff coefficient and the drainage area. But the volumetric runoff coefficient is only based on the impervious area, not on the pervious. It only assumes an impact on the impervious area. So again, what's really underlying each of these methods, whether it's curve numbers, whether it's volumetric runoff coefficients, is that assumption that pervious areas are pervious, that the water is infiltrating into the ground, and that we don't see a substantial amount of it showing as runoff. Again, we're just basically assuming that that part of the sites just don't have a huge impact on the capacity of our design systems, since the system is already having pre-development runoff where that was actually really pervious area. And I'm going to hit the bandwagon that says we also really don't do a good job with systems analysis, where we've looked at interactions of multiple SCMs discharging, and we're also not investigating natural water resources and the behavior of existing sites. And I'm going to really focus on this when they talked about urban soil health and asked me to do this. I'm like, oh, good, I can talk about urban development and where we are. Because we're seeing more of this. And I know that Ellicott City has seen this. You know, this is just the impacts of a storm we had in 2017, where we got 4.71 inches in 85 minutes. This is our campus entrance right here. This is actually a stream. And again, you can see the car that is trapped here and then throughout our borough. And in fact, you can see this is early in the time where the underpass is filling up. And this is actually our underpass filling up. And it actually overflowed the underpass. And there are sag inlets in the bottom of that underpass. It overflowed it and became, effectively the street became a broad crested weir and flooded about 3 blocks down where people were kayaking down the street. It's a summer thunderstorm. This was not a tropical storm. This was not anything that was predicted. And I was 20 minutes away and we got a shower. And so these are the things that we're seeing much more frequently, whether it's Baltimore, whether it's Harrisburg, Lancaster, whatever. And so the question I was asking and the borough asked me to look at is, what could we do? What are the things that we could do? But because we're seeing more of these, this is actually our rainfall. Tropical Storm Lee is our storm of record. And we got, you know, about 350 millimeters, about 14 inches over about 4 days. You can see the spikes in there. This is the storm I was just talking about, 4.71 inches in about 87 minutes. 2 years later, we got about 56 in about 60 minutes. And in this case, we got just under an inch in 17 minutes. And so if you think about it, this was just under an inch in 17 minutes. This was just the front end of a storm that's in this higher intensity area. So again, and that's going to come up a little bit. So you think about this as a 1 inch in about 15, and this is about 4.7 in about an hour and 20. So roughly, this is just one of those, a quarter to a fifth of that storm. And then we got this, so we took all of these things that we got and we plotted them on a map and took a look at that. I will say that the clouds are that 4.71 inches. The skulls are the Halloween storm, because that's why you have to put skulls on it. But when I started looking at that, you can see that this is in a line. I'm like, there's something going on. It's not flooding everywhere. It's flooding in very, very specific locations. And so what I did was I actually went back in, because I'm also a nerd. I went to the State Museum and I pulled down some of our historical maps, and you can see it in the background in here. There are streams cutting through here. There are streams cutting through here, and you can see basically and down through here. Effectively, what has happened is that the existing stream network has now been buried into our sewer pipes. And probably have to check off some of the animation. And that's what's happening, is it's buried in our sewer pipes. So now we've actually got water already in our pipes that's flowing continuously. And I just wanted to make sure I highlight these were, highly modified. This is the outlet for what we just saw. We used to have a canal running through here in a mill race. Those are actually dug out, filled back in. We don't know what they did. In some places we found coal chips, we found oyster shells. So what we're even thinking is an urban soil is really not even an urban soil that we don't know about in these old historical areas of town. And I don't think Middletown is alone. I think that we're going to find this commonly throughout the watershed, given the age of many of our older cities in this watershed. And so the question we were asking as part of this is, how does this historic development affect what's happening now? And we really need to be looking at the hydrologic cycle of urban systems, and this idea that there was substantial modification of natural soils even before we had large scale heavy machinery. Some of it could have been hand dug, some of it could have been plowed, but we really have been doing modification of these soils in many areas of the US for 400 to 500 years. Because what's going to happen with that, what we really were thinking about is that we've got these pipes running through several areas in town where we've got a stream flow already in the pipe. It's going to have some additional flow coming in as a function of rainfall. We also likely may have some shallow groundwater flow that's going to flow laterally or almost laterally. It's going to intercept some of our older pipes that are not intact. And then we've got stormwater coming in from existing development. And if we add new stormwater, or we have these larger storms, these very intense, high intensity storms, we're going to have that flooding. Because again, we need to be thinking about all of those contributions, particularly in these areas where we know our pipes are capturing existing streams that have now been buried underground. So I'm going to come back to one piece of this. I want to highlight some of this through modeling. And we are doing field work, and I'll talk about the field work at the end of this. But this is actually our dormitory area where we have good information on the piping system. So this is actually a part of our campus that exists. And we want to look at a couple of questions coming in here. Again, about 20.4 hectares, 18 subcatchments, 1 to 12% slopes. We looked at 3 design events. Again, a SCS type 2 design storm. We put our tropical storm Lee through it. And that 2017 4.71 inches in 87 minutes. And for each of these, we looked at different increments of rainfall. 15 minutes versus 6 minutes, 1 hour versus 1 minute. And the idea is if we have this many sub watersheds or this many, say, individual lots or groups of lots that are aiming for a street inlet, how are these models working as we start looking at these drainage areas have very short response times? Did it make a big difference with that? So taking a look at that, when I started looking at that for volumetric runoff coefficient, in terms of, and these were all swim modeled, when I looked at that, the volumetric runoff coefficient, nothing made it didn't make a difference what the time increment was, whether it was 15 minutes or 6 minutes for the SCS storms, 1 hour versus 15 for Tropical Storm Lee, or 1 hour versus 1 minute for that microburst storm. But what it did make a difference on, and again, if I was thinking about the Maryland design criteria for water quality, the volumetric runoff coefficient makes no difference in that respect for what the rainfall time is. But what it did make a difference is in the time that the nodes were more modeled to be flooded. Again, where those manholes effectively would have been on the surface potentially, or potentially running on streets and that. So the SCS, we didn't see a huge amount, but on that 1 minute response, you can see that time that was predicted in a 1 minute storm. And why it's happening is what makes logical sense to all of us sitting here. Is that it's not like we put a slug of rain onto the system and wait 15 minutes before we add another modeling of the system, or we take that one slug and we divide it out over time. By putting new rainfall increments on top of the system, the piping system, the land system every minute, the model is actually capturing that compounding rain impact on the system and on our ability to model the system. Because again, 1 hour, it shows that we had no flooding. And I know from the pictures that my grad students took that we had flooding. Pictures the borough took, we had flooding. So we have to be talking about what is the appropriate rainfall time increment that we're putting into our models. Like I said, and we're continuing to look at, again, in the subsurface, where does this water go? Again, if we have a compaction layer, and we just showed the picture earlier, we saw one that's about 2 to 2.5 hours, or 2.5 inches down. Boy, it's been a long day. And we want to know is that, does this continue to be deep groundwater replenishment? Or if we trap water in a basically what I would call is a shallow dish right here, propensity wise, is it going to try to flow laterally until, for example, it finds a utility trench, or it finds some sort of a fracture in the soil, or it finds a pipe? So again, are we actually getting into our storm pipes, and particularly in these more intense storms, are we actually getting substantial contribution of what in sanitary sewer systems we would call inflow and infiltration? So that's the question that we're trying to raise with some of this. Again, we've been through this part. Again, we really need to be thinking about compaction coming in here. We saw this earlier, compact versus non-compact, as opposed to saturated versus dry. And so we're actually out doing a lot of measurements on various sites in Middletown, and we'll be extending this into Baltimore in the next few weeks. Again, we're doing cone penetrometry measurements to try to push down and find out how deep is a layer. We hit a resistance to 300 psi, which 300 psi is considered so compact that root growth is poor to non-existent. We're actually looking at surface surface resistance to penetration, and we're doing double ring infiltrometer tests. And I just wanted to highlight this over here. This is one of my neighbor's properties, who's very nice to highlight this. And all of these numbers here are the depth to where we hit 300 psi. There's the garden that she and her husband had been tilling, but you can see over in here, we're ranging between 4.5 to 1.5 inches. There's not a lot until we hit a compacted soil. And this house was built and the yard hasn't been changed a lot since the 1800s. But you can see here where the sewer pipe runs, where it is wet, and they've also got a leak from their little pond, that once the soil is wet, we're actually getting really deep penetration. So we're able to get that layer where we actually might have water move. This is a park, again, that was effectively created when they buried one of the streams in a pipe. And the white was taken after we'd had several weeks of dry weather. And then we had a decent rain, and we went back out and remeasured compaction after the rainfall, after it cleared up for about a day or so, but just see what happened with a little bit more moist soil. It's never been developed for anything but a playground, and it was part of farm fields for decades. But you can see, importantly, one is, again, is that you can see how much different it is when the soils had some moisture in it. So it is acting as a bowl, but it's acting as a leaky or permeable, kind of like when you're, paper plate, why they advertise Chinette, for those of us who are older. But that leaky paper, cheap paper plate that would kind of leak the barbecue sauce through. So we are getting some additional penetration when wet, but that is where we're coming at that from. Again, you can see that difference. But initially, after several weeks of very dry weather, we just don't have a lot of depth to hold water. So back to our study, I'm not going to go through the rest of it, except to say that what we did now was we modeled infiltration, looking at 2 compaction scenarios using some of the data we measured in the field in that park. And you can see our Horton infiltration rates. And then we pulled our compacted soil information from the SWIM hydrology manual. And I wanted to I'll highlight that in a second. We also plugged in 2 water storage depths I'm going to get to, just so you know. We plugged a 1-inch depth and a 2-inch depth. And if you think about it, that's the amount of available water storage in the soil. So that's really deeper than that in a soil profile, because you would have, obviously, that would be the porosity, the effective porosity that's available over a larger depth. We did run it through 6 storm events in April 2020, where we basically got a 1/2 inch of rain over a month and no flooding. Did want to run it under the current and climate scenarios, and then the July, the microburst storm we've been running with, again, the July 21, where we had effectively 1 inch in 17 minutes, and then Halloween, because we just have to run Halloween storms because that's what one does. And I'm coming at that because people have asked me, why did I use Horton instead of green and amped or curve numbers? And I did it because SWIM's got a limitation and other models have a limitation. If I'm using Horton, I have a max volume I can put in here that effectively it acts as a barrier and says, once that volume is full, effectively, like anything else, it's going to run off the soil and it's not going to infiltrate into the soil. It's not going to put any more in. If I come over to green and amp, that limitation is not there, and it's not there in the curve number method. So Horton is the only option that gives us that restrictive layer. And so the question is how important is that restrictive layer? And this just comes through looking at the runoff coefficient. Again, you can see the depth to that restrictive layer, and then compaction, which again would affect effectively the porosity and the rate of flow. So it's kind of this combination of one, we've got basically a shallow dish, how shallow is the dish to hold water, and then how fast can water get into the soil. So if we come in, as we would expect with the storm that had no flooding, we really have a very low volumetric runoff coefficient. Interestingly, with the SCS design storms, again, these are 10-year storms because that's what our design up here is. So we run them with a 10-year storm, even under the, now in with the climate, that effectively what we see is that the runoff coefficient goes up based on the size of the bowl we can hold water in. Interestingly, as we start getting into these other real storms with these very intense storms, that the runoff coefficient is a function of how much can the bowl hold when we've got a very shallow water depth. But if we have a little bit more water space, you can see these two are different, which is, again, the severe compaction has got a higher volumetric runoff coefficient compared to the one with the normal one, where we can get more water in. So we can see that at some point there is an interaction between porosity of the soil and basically how big is the bowl. So that's what we're coming in with. You see the same thing coming across the Halloween storm. So this is kind of showing that there is that interaction. And we do it and take it to what we really care about as engineers, at least what our clients care about. And we come back in, this is basically that node surcharging and conduit surcharging. And we can see that those differences are showing back up again for some of the storms, depending on what it is. We are likely going to see an interaction of how fast can water get in the soil and how much water can the soil hold. And I did want to summarize it at the bottom. You can see down here the 1 inch depth of limited porosity versus normal 2 inch limited porosity. There's the difference in runoff volume. In the case of 1 inch depth, the porosity had very little impact. It's going to be the same thing. It had a little bit of more impact on the flow rate modeled, but it certainly has a difference. We start getting to 2 inch, basically the ability to hold more water. So that's really the important factor as we start getting into that piece of it. Again, because several of the models come back in and use curve numbers as a design criteria, I took this model data and went back into calculating curve number. So I wanted to show that impact of curve number. I only did it for 4 storms, basically the newer SCS curves based on the recommendations, not the typical type 2. Then added the climate scenario using the Marissa data for a multiplier. Our 2021 4.71 inches in 85 minutes, 1 minute rainfall data. And that's the July 21. That's the 1 inch and 17 minutes, 1 minute data. And then the 2017 4.71 inches in 1 minute. And we did come through, and again, you can see the normal and the compaction and for the 2. And then I also put in here, importantly, again, I'm using Pennsylvania criteria. And thinking about the campus where you saw the picture initially, there's a lot of open space. So we could model it as open space in some of these larger landscaped areas based on the criteria we're given. And I put in there then the curve number for poor, fair, and good condition. And that would be, again, there's good, there's fair, there's poor. First thing to see is that open space is not the right way to describe our campus landscape, because all of our curve numbers predicted from the modeling are higher than that. And if we're using that lower curve number, we are under predicting how much runoff we're actually going to get. Also, importantly, coming back in, we can begin to see what we saw earlier, that our curve numbers are actually going to be slightly exceeding 90 if we are looking at a 1 inch compaction layer depth. So basically a 1 inch water storage layer probably is going to be between 1 3/4 and 2 inches of soil depth before you hit that 300 psi. We're over 90. We're actually effectively, it is acting very much like an impervious space. And if you think about that picture I showed you earlier of our campus, that's a lot of land that is now acting much more imperviously than our models are predicting. That means we're getting a lot more flow and we're not getting that infiltration. And again, we can come back in and see it. I actually then said, okay, so what if it is effectively, what would give me a 90 on B soils? And effectively it's 1/8 acre residential lots, and you didn't see that many buildings on there. So again, or I could go to open space D soils for that 2-inch water storage, but not for the 1-inch. So again, it is critically important we start thinking about how we're modeling and how we're predicting how much flow is going to end up in our piping systems, heading for our bioretention. If the lawns are draining to stormwater treatment systems, we cannot be assuming in many of these older urban areas that we have the ability to say that what looks like grass is actually pervious. It's just not that pervious. What is important also on the flip side with that is as I tie this up, there's a lot of good work out there from Stu Schwartz and others talking about soil restoration. But actually this, and he's done a lot of work looking at deep soil restoration. This actually gives some hope that maybe even shallow restoration in areas where we can get that type of infiltration, that even shallow restoration might get us some additional soil storage that we could use. And these are things we want to think about, how if we've got enough space away from building foundations, away from transportation infrastructure, to think about, are there places where we could do some soil rehabilitation to getting us water storage that's closer to 2 to 4 inches instead of that 1 inch that we're seeing now in a lot of places. The other thing we're trying to do with this is to be trying to see if we can relate, for example, since right now Horton's equation is the only one that lets us put a restrictive layer into the model. Could we predict Horton's infiltration coefficient, final infiltration coefficient, as a function of the cone penetrometer? It is still messy. We are going to be extending this down to other sites, but boy, they're landing around somewhere that there might be a relationship, even if it's a weak relationship, that we could begin to get a handle to predict modeling some model parameters based on that simply a cone penetrometer test where we could do a ton of them in an hour or two on a site and get some idea of how that site is going to behave before restoration, or if we can go in and do restoration. We are continuing to do soil monitoring. We're going to be extending this out. And I do want to highlight again, just from a moisture content, what is this impact of the compaction layer? So this is our old water treatment plant. And you can see in here, there's a discontinuity layer of what looks like a red clayish material at this site. And then at our park site that I just been showing you pictures of, this is, and you don't see that discontinuity layer. And this was a January 23 storm. And you can see the sensor, the top sensor is in at about 3.5 inches and the bottom sensor is at about 7.5. They're very close to each other. They're the same top and bottom because we want to be above the compaction layer here. So this is just above that sensor and then down below. And they are at the same depth at each of the two sites. But what you see very quickly on the park site with no soil, with no discontinuity layer, no compaction layer, what you see is that the top and bottom sensors track each other very well and very quickly. But at the water treatment plant with this compaction layer, we get a response in the top layer, but we do not get it in the bottom layer. We get very little response until we get out here and get more rainfall. So it goes back to what we were seeing with the modeling. What we're seeing with the modeling says we may not get past that compaction layer in a short, intense storm. That thing may be acting as an impermeable bowl, and a very shallow impermeable bowl. And that's what this is indicating, is that, yes, we can see it over time, which the model does not account for. If we can get that compaction layer a little more saturated, it will begin to transmit water through and down to the deeper soil profiles. But it is going to take getting that layer wet in order to do it. And because it is compacted, it is going to very slowly percolate water through that system. And just to highlight that, this is our water treatment site where you just saw the pictures. Their stack sensors are approximately here. We've got a downslope sensor by the creek. And we've got an embankment sensor up top, and I'm going to put the sensors up here. Again, so what you just saw were the vertical sensors, and the other picture, different storm. This is a March storm, but you can see how long from the top in that center area till we get the reaction in the bottom sensor to get through the compaction layer. There's that piece. The embankment, as it's coming off the side of the slope, is the bottom of the toe of the slope on that area. it's there, but importantly, the downslope sensor. So water is coming down through that swale, very open. That's actually the old canal, or mill race. I think it's mill. That's a mill race. That's the old mill race that was never totally filled back in. But you can see that downslope sensor, you can see how much longer that we have a higher soil moisture. So it's a very strong indication that we do have very active lateral subsurface flows. And again, those are those subsurface flows that if we were to intercept a utility trench, we were to intercept piping systems, where we're getting water into our systems that we are not accounting for in our models. So I want to tie this up with this idea that effectively we've got this conundrum for urban soils. They need to be structurally sound for infrastructure, but we're asking them to do water quality and water quantity treatment. And this is really hard to do in these very tight urban areas. For water quality, we need to be looking at contact time. We need to be thinking about, what's going on chemically. Again, if we're going to get nitrogen removal, we really need healthy vegetation and healthy soils. Phosphorus conditions, phosphorus is typically heavily dependent on what our soil composition is. And road salt changes the game totally. It's going to change our rates of removal of nutrients and metals. When I start thinking about soil structure and infiltration, again, we're going to get those lower rates in compacted soils because we've got to reduce porosity, because it's what we want. We don't make compacted soil for structural strength. We do not want water penetrating it. So we have that. But if we're outside of those areas where we want compacted soils, we've got this reduced porosity. We have a limited infiltration volume, and that's going to change our flow rates. It is likely in some of these areas that our curve numbers are underestimating are totally underestimating our stormwater runoff for both peak flow and volume. Again, soil storage was important in these lower parts of the storm. Is that a 1-inch depth, a 2-inch depth? We hit that compaction layer, whatever that is. And our models really aren't doing a great job of reflecting that behavior. They likely underpredict those urban soils and turf grass contributions to runoff in these intense storms that we're now seeing more of. And again, this would be okay if turf grass and these spaces were not, or a small part of our urban landscape. But that's not there in these suburban areas. We're talking 35% of a suburban watershed. That's a lot of land that is generating runoff that we have not been as good at predicting. But we do think there's hope that we can look at soil restoration, maybe to a few inches, that we can get some benefit from that. So again, as I said, we're tying this up by continuing to investigate the possibility of looking at permeated or compaction testing to roughly estimate the Horton's number. But I do want to leave it with these old urban systems do give us many, many challenges. Buried streams, incorrectly mapped infrastructure, development, redevelopment, rapid stormwater responses. And I want to make sure I tie it up with acknowledging a lot of the support. Currently, the work is funded by the Pennsylvania Sea Grant Program. 2 days ago, I think it was, or today, that we get our Chesapeake Bay Trust money. We'll be moving this down to Baltimore, and it will be part of the Baltimore Social Environmental Collaborative, which is funded by the Department of Energy. Feel free to email me, but I will say, I'm going to tie that one last slide. I want to close with this one. This is from an NPR story that was done on tying into this project. And it does talk about the 2017 storm, because when I think about it, I've talked a lot about water flow. I've talked a lot about water quality. Everything we do with this obviously has a human impact. And I thought that I would highlight this. My neighbor up the street a couple of blocks had thought that Tropical Storm Lee at 14 inches over 4 days was bad. But then the 2017 4 inches in 87 minutes actually took everything in the basement that was still down there and filled it up. So they opened the basement door and the basement was full. So these underdesigns, these misses of these numbers and not understanding shallow subsurface flow has this potential to have a huge impact on the people that we're really trying to design infrastructure to protect. So with that, I am going to open it up to questions.
Thank you so much. Before we jump into the Q&A, and I see we have a lot of great questions in the Q&A box, I'm going to put the survey link in the chat for anyone who might need to jump out early. The survey is really short. It should only take you a couple minutes, and we really appreciate it. So I'm going to move through the questions in the order that they came. So our first question, does soil texture dictate the loss of permeability with the salt application?
Okay, texture itself is actually a size classification. The answer, except for clays, is the answer for clays. If I was going to answer strictly on texture, the answer is no. However, typically our silt range soils typically have that organic matter in it. And so it's typically not the sands that are unreactive. So texture is not a direct classification, but in some respects it probably is because of what the composition of the soil in the smaller fractions is. So that's a good non-answer.
Our next question, do you think any of the following help reduce the quantity of stormwater runoff from turf? And some of these options: gentle terracing to still allow mowing, mechanical aeration 2 times per year, or surface application of compost 2 times a year. Let me know if you want me to go through them one by one.
Oh,
again.
no, I've got them. I'm just trying to decide how. We are actually looking at aeration. The early results that others have done have said not really. Surface application of compost, probably not. A good cover crop would do it. Terracing, probably not. Again, we just got to quit compacting the soils and where we want to infiltrate. If you were talking about coming in and maybe scarifying down to a couple of inches, there are, Washington State, for example, has regulations on new development where away from the buildings, and I've forgotten what the distance from the buildings is, I'm thinking about 10 to 20 feet. Outside of that, the contractors are required to go back in and scarify and mix in compost, some fraction of compost, down to, I think it's 6 inches total between the two. Again, so instead of putting a topsoil layer back on top of compaction, they've actually got to scarify it into the soil some to try to get a little bit deeper. That's going to be more likely to work, and that's something we're actually checking on to try to understand that. Again, Stu Schwartz has done a great deal of work looking at different depths, but our focus is going to be trying to look at that very shallow urban soil structure that we can actually do in cities outside of being able to do it on parks and that we could get around houses or land development.
And then what about compost? Did you say that?
As a surface layer, that's not going to do anything. I mean, you've got to scarify it. You've got to it's got to be incorporated in. You can get it into the soil. So like through scarifying and mixing, yes, because you're going to gain back some storage space, but it can't just sit on the top.
Right. Okay. Would it benefit to grow wildflowers and other indigenous plants in place of turf grass? If so, what would be the best way to begin, particularly for large lawn areas?
Okay, so the first thing, let's say I am not a plant biologist and I do not play one on TV. Anything that is deeper rooted, absolutely. Anything we can do to soil health is a function of being able to tear up the compaction or not compact in the first place. So again, a lot of our indigenous plants and flowers have deeper roots. You saw the picture from Prince George's County, Maryland. That I'm not sure how I inherited it, but hopefully it was Prince George's County because I got it from somebody else. That's why I put that. That's the tag I put on it. So anything where we can get that kind of deeper rooted system, even if you can go to a prairie grass or a native meadow grass that's native to this area that has a longer root structure, that anything will help. Because again, over time with that and the biologic community and the earthworms and all that, we do begin to get some recovery. But it did kind of scare us up here in Middletown that even in some areas that were developed in the 1800s, we're not getting that far down in terms of compaction. Because Bob Pitt's work had shown that at about 40 years down south, they were getting good recovery. That may be the difference of fire ants versus earthworms. I don't know. But they can keep the fire ants. I'm not really sure I'm willing to trade that off. I grew up down there. No.
Thank you. You'll have to forgive my pronunciation of this word if I mess it up. Have you ever implemented the Gwyn soil restoration technique?
Have not. I would love to be able to test it and see if we could actually get some data on that. And I know others have, but I would love to get into it.
Can you speak on what that is a little bit more for anyone who might not know, as well as myself?
I would have to exactly look it back up, and I have it, because that's not what I'm as familiar with. I used to say.
Yeah, no problem.
Play a second, and we're going to do this with Vanish having 2 monitors. Can you spell that again? Because my memory's going.
Gouin.
Spelling would help.
G-O-U. Wait. Yeah, that's the spelling we have here.
Yeah, I would have to come back through. I'm just quickly glancing at it, and I've heard people talk about it. It's a huge incorporation of compost. In some cases, again, I would watch the amount. I don't think that incorporating compost and bringing back in organic matter that's going to support plants, I am not against. I'm never going to tell you that I'm against that. It looks like it's basically an inch and a half, and 1.5 to 1 inch of compost, and then steel rake. Let's see, I'm trying to read through.
And I think the person elaborated, ditch
Please.
witch rows with pine fines.
Again, if you can get in there and start basically creating a higher porosity soil, the better off we are. So I don't have a, that's, again, in a ditch which will get down several inches. So if we can do that, I was thinking more of a scarifying, kind of the soil tearing up is the one we've been talking about with people about trying to test after they do it. But that is something, yeah, I don't have anything against it. The biggest thing I have, my concern, it goes back to the water quality aspect, is to think about how to balance that out with how much compost goes in. Because even if we just tear up the soil and we don't add a lot of compost, we're going to gain some benefit of just simply having porosity. There's a paper that was just released out of Los Angeles County, it's a UCLA faculty, and they were talking about being near transportation infrastructure and looking at how much sand they'd have to add to get back infiltration. That's a good water quantity issue, and that sand could do it too. It won't get us as much in the organic that we need for plant growth. So again, it's just kind of that balancing act that we're looking at.
Thank you. We've got 2 more questions. Have you considered using the LID controls in SWMM to reflect a 2-layer system with green AMPT, green amped?
I have looked at it. That's the next step. I'm bringing on a PhD student this fall. That will be the first project he tackles. So we've been looking at doing that. Part of the work going into Baltimore, it's going to be to get some deeper probing and get some deeper sensors in. This one in Middletown that we've got, where we saw the compaction layer, where we're able to dig into the soil, it has a very shallow compaction layer, at which point it releases back to being a it's a more native soil. It's not as compacted because this was basically where they packed down the canal, the mill race, so basically it didn't leak water. But if we got into, if I were to go back to my original, I'm going to go back over here. I know it's still screen sharing, but let me come back. I'm going to go back to your Prince George's County picture. There's not a lot in here of what we're going to get through that type of compacted soil. So again, we're still going to have a reduced porosity. Yes, we could do it as a 2nd layer model. I might be just as good at that point of trying to work with the restrictive layer in Horton. If I was looking at, let me flip ahead, sorry to be doing through, give somebody eye problems. In this case, where again, we've got this restrictive layer, but again, below it, this was where they tried again to pack down the canal so it didn't leak water. Again, this was built in the 1700s, so it was all hand done. But you see, it looks fairly porous up here. It's fairly porous here. Below that, if we've got a very shallow, basically restrictive layer, kind of like a fragipan, and it's not that thick, we could potentially do it as a 2-layer system fairly easily, 2 or 3-layer system fairly easily. But again, if it's a big block of compacted soil, I'm not sure we would gain a lot of benefit from that additional modeling.
And our last question in the question and answer box, can you elaborate on the Horton filtration rate outlier for site under construction?
Do I totally understand what's going on with that? The question was this guy over there. They were in the middle of constructing they were basically expanding our new detention pond. And they were under construction, and I told the grad student, please don't go out in construction sites, but the tape wasn't up, so he went in the construction site. So it was the one that fell out of that. We're still trying to understand what's going on. We actually did retest it this summer, and I'm trying to think, I think it's this plot right here. After about 3 years, this is about 3 years ago. Over here, that blue circle with some current work students did this summer. So it is coming back toward the line, and we think it is because he hit a weekend when it actually had bulldozers everywhere. What's very interesting with that site is that we got a very high depth. So it was freshly compacted soil and a very low infiltration rate, which likely means is that it's, I'm going to come back in him. No, I'm going to get that. Where is it? This guy. It's likely going to be something more along the lines of we're impacting the porosity of the soil, as opposed to having a restrictive layer. So that's what we think is going to go on, is that it's actually just so compacted from that construction that we've got a very low porosity, but we may not have a restrictive layer, because that is designed to be a very slow infiltrating pond. And again, they're middle, there's a whole, that was tested pre-pandemic. But it's interesting that in several years, a retest of the site put us closer to the line, saying that over time, whatever stabilization of it's doing naturally, because trust me, our maintenance crews are not doing a lot with it except going out and mowing it, that it's coming closer to that line we're hoping we can use.
I have one question just to wrap us up. So from your experience, for those involved with the design, inspection, maintenance of BMPs in urban areas, what do you think can you give a top 3 considerations that that folks should keep in mind? Maybe one for design, one for inspection, one for maintenance when it comes to urban soil BMPs.
So obviously, even for the BMPs or SCMs, the biggest things I would keep in mind for design is that if these things are draining pervious areas, they're not pervious. You are likely to be getting more water in there than you're planning on. We're also looking at how these things are going to perform under climate change scenarios. So what happens when we start bringing more water into these systems than we planned on from a design criteria? When we start doing that, we get less treatment because you do need that contact time. And so we're either getting bypass or water is pushing through these systems a lot faster, which means the time that we design these things for, even though technically time is not showing as a design criteria, it is in there as we calculate flow rate. That as we design, as time is a parameter, the less time we put this waters in these systems, the less treatment we're going to get. With a balancing act of something we're looking at, but we're not real far along on, is that what happens when we have these 3 or 4 week dry periods and these systems sit stagnant. There's also other things that are going on in these systems with bacterial interactions and soil interactions that could also be reducing treatment effectiveness because it's changing the oxidation chemistry that's going on inside these systems. I'm trying not to go too far into chemistry, but that is going to be a problem. But again, if you're designing these things that are taking grassy areas, you're probably getting more water than you planned on. And that's going to reduce the predicted efficiency. Design, inspection. If you've got areas that are supposed to be planted and you've got areas that are problematic and this is not growing, I would probably be looking to see if there's a problem with the soil health itself. Could be that if you're next to a roadside where you do see a lot of areas that are kind of gray and dead, it probably could be the road salts are sealing that soil and the plants can't go there. So again, visual inspections of plant health are possible in that. And then maintenance. I'm going to go back to, I think we can do some things with trying to even just tearing up the soil to a couple of inches. Again, don't do it next to your foundation. We don't want to have you have what happened to my neighbors, the basement full of water in these intense storms. But if we can get away from that, if you've got a larger lot or you've got a downslope and you can do that, and you've got the potential, again, one of the challenges we're working with Baltimore on, and also Middletown, is understanding where subsurface utilities are. So how much do we have to know exactly where the utilities are? Because if we actually put more water in the soil and we get lateral movement, are we going to cause a utility problem? And that has to be a serious consideration. How do we deal with all of that? Because there's a huge amount of infrastructure that already exists and some of it is poorly mapped. So are there these places though that we could come out and do this? Could we even go into park areas? And maybe we can't do the 2 feet or 1 foot that Stu Schwartz recommends, but can we get some benefit to go down to 4 to 8 inches? What can we do? Where does it fit on grassy medians that are draining that direction? Versus again, needing to keep structural soil strength in certain areas because of the fact we don't want these things falling down or falling in. So I don't know if that totally answers your question, but I hope it helps.
No, absolutely. That was great. We had one more quick question in the chat before we close out. So the last one was dry bulk density of the soil can be considered as an indicator of the compaction. What is the average bulk density of the soil to be considered as compacted? If you have that.
The last time I looked at off the top of my head, if I'm remembering right, the suggestion was that you start getting somewhere above about 1.85 grams per cubic centimeter. I think it's what the agronomists consider to be compacted. We're doing our own measurements. I don't have the data handy, but we are doing that testing in there as well as soil texture analysis to see what impacts texture has. But I will sit down and say my undergraduate student is taking a vacation before school starts, and I'll be back at this stuff in the fall. Our bulk densities we were seeing on these early sites we were testing, off the top of my head, was about 1.8, 1.7 to 1.8, if I remember right. So they're on the borderline. But we're also, the problem we've got, I'm gonna skip back 2 slides. This is a long answer. Let's get back to this one. We're trying to come back in. One of the challenges we're having is that this is like, for example, in this slide, that's that restrictive layer. So trying to separate this out to measure the bulk density of this layer to understand, because that's our restrictive layer, whereas this is testing up a little bit higher. It's just we're trying to get cores that'll give us some information, or trying to find places where that compaction layer is thick enough that we can get that bulk density information and understand it better. But again, the agronomists, others recommend 1.8 to 2. You're really pushing that compacted soil pretty heavily, and you're just not going to see the root growth. The ag people have a lot to tell us.
Absolutely. Well, thank you so much, Shirley, for taking the time out of your busy schedule and for such a fantastic presentation and some great question and answers. And thank you, everybody who stuck with us to the end and for your great questions. This recording is going to be up on the website in the next couple of days, so keep an eye out for that. And again, the survey is in the chat.
And thank you to all the people in the chat who said thank you.
Yeah. All right. Well, have a great rest of your day, everyone. And thank you again, Dr. Clark.
Thank you. Bye.
Bye.